other strong acids, HCl, HBr, HI. Some would consider HF strong, and then H2SO4, HNO3, and the very dangerous and explosive perchloric acid. Those are all be considered strong, and what that means is, again, upon reaction of any of these acids with water, we get complete conversion of the acid amount into hydronium plus whatever the conjugate base is. Technically, these are all equilibrium reactions, but for your strong acids, we can ignore the reverse arrow, and thus the hydronium amount is directly related to the original amount of acid. 23, if we have a solution which is acidic, we're going to have more hydronium than hydroxide, and we will be acidic. And again, anything below 7, we're trending acid. As we go above 7, we'd be trending basic. 24 is strictly using calculator to take the negative log of the given hydronium. Calculator spits out 2.55, which is rounded to A, 2.6. 25, there was no correct answer, so everyone got credit. What we should do to solve for hydronium when we're given Kw and hydroxide is to plug in Kw at 1 times 10 to the minus 14th and divide by the given hydroxide at 2.8 times 10 to the minus 3, and that should give us 3.57 times 10 to the minus 12th as your molarity of hydroxide. That's relevant because this is a much smaller number than the amount of hydronium, so you can check yourself. The pH of this solution would again be 2.6, quite acidic. Which of the following has the greatest pH? So now you're looking for the highest concentration of hydroxide. It's not going to be either of your acids. And sodium hydroxide is a strong base, while ammonia, even though it does make some hydroxide by reaction with water, the reversibility and the low K value for this particular reaction suggests that a 1 molar solution of sodium hydroxide, which fully dissociates to make 1 molar sodium hydroxide, will have the highest pH, and that pH, like we did in lab, will be very close to 14. So sodium hydroxide, 1 molar, really high pH, caustic substance, hazardous to mucous membranes, good at cleaning a drain. Sulfuric acid and sodium hydroxide, just writing the equation. This is classic acid base or double replacement. We know we're going to move protons. If we look at sulfuric acid and break it up, so to speak, and the same with sodium hydroxide, this very much going to help you identify the product as water for one of the products and sodium sulfate for the other. Balancing the equation suggests that if we really have 2 protons and we really have 2 hydroxides, we're really going to make 2 waters. So there's your balanced equation. And if we use that balanced equation to say if we mix 1 mole of each of those acids and bases, the recipe says you need 2 moles of NaOH for each mole of H2SO4. Therefore, this 1 mole runs out first, making it the limiting reactant. And once it's gone, you'll have half a mole of H2SO4 left over, which is going to reflect acidic conditions in the resulting mixture. Rate of reaction is affected by 4 things. The nature of the reactants is probably the most important. Temperature, pressure, also can affect reaction rates. Activation energy is a huge factor in reaction rates, and remember, it can be lowered by a catalyst. Surface area and many other factors do affect how fast a reaction goes. The equilibrium constant for any reaction that starts with reactants and makes products is K. That's the equilibrium constant, or KEQ. Before we talk about it, we should define what an equilibrium means, and that's when the rate of the forward reaction becomes exactly equal to the rate of the reverse reaction, such that the amounts of products and reactants are not changing or are constant. Once we've achieved constant, not equal concentrations, but constant concentrations, then we would be at equilibrium, and then the value of the equilibrium constant, which is the concentration of the products divided by the reactant supplies. So the larger the value of K, the more products there are. The smaller the value of K, the more reactants there are. For reference, if K is 1 and it's a very simple reaction with no coefficients, then we would say the products and reactants are equal once the system reaches equilibrium. And Le Chatelier says if you have a system at equilibrium, if you stress it by adding a reactant, the equilibrium will shift to make more product. If we have a strong acid and a weak acid of the same concentration, the strong acid is going to make more hydronium and have a lesser pH. Phosphoric acid and sodium hydroxide. Again, with this, we want to scribe in formulas for phosphoric acid. We're going to derive from the proton and the polyatomic ion phosphate. That gives us H3PO4. And for sodium and hydroxide, our formula is sodium hydroxide. These two again react with each other because acids all have protons and like to give them away. Bases often have hydroxide, and the hydroxide is perfectly willing to take in a proton, and when that happens, we make water. The other product is the sodium ion and the phosphate ion, which bond in such a ratio. Balancing the equation says these three sodiums are now matched with those three. We now have 3 hydroxides and 3 protons, which balances with 3 waters. In the titration problem, 0.15 is the molarity of the sodium hydroxide, and during the titration it takes 0.0153 liters, and therefore the moles of hydroxide needed to titrate the sample are 0.15 times 0.05, 0.15 times 0.0153, and that gives us 0.002295 moles of NaOH. Getting over to what we're interested in, the phosphoric acid, it's a 1:3 ratio. So we can divide by 3, and we're now at 0.000765, and that's the moles of phosphoric acid. And for the molarity of phosphoric acid, we just take those moles and divide by the liters of the sample. 5 milliliters is 0.005 liters. and we end up with a molarity of 0.153. Sulfuric acid has that formula and it's considered strong. That's because of what it is, and diprotic. And having 2 protons for sulfuric versus 1 does not make sulfuric stronger. In fact, both of these acids are strong acids. One's not really stronger than the other, so for 35, the answer is false.